Okay, let's move on. So we talk about the subthreshold here, and we see the straight line. And the straight line has a slope, and we call this subthreshold slope S factor. So this S means what? Means the slope. Or in other words, if you look at the unit for the S, typically it's like millivolt per decade. So what does this mean? That means if you want to reduce the current by 1 decade, which means 10 times, you need to reduce your gate voltage by S millivolts. The S, for example, can be, let's say, 80 millivolts. So that means if you want to reduce your current by 1 order of magnitude 10 times, you need to reduce your current by 80 millivolts. So I should say that the S factor actually is 1 over the slope. It's 1 over, and that's to be accurate, it's 1 over the slope. The slope here is, the log ID. This is based on log 10. And then respect to the gate voltage change. So it's a derivative of the log ID respect to the gate voltage. And then it's 1 over that. That is the slope. And it has a unit, millivolt per decade. If you reduce 10 times of current, you reduce the voltage by 80 millivolts in this case. So why is this subthreshold slope important? Because it will determine a few parameters. So think about that. You have another transistor technology, maybe offered by another foundry, right? Then it may have the curve like this. So it has a less steep slope. Maybe this S will become like 100 millivolt per decade. So this is less steep, even though you have the same like on current. So here, for example, you still have the same on current, but the slope is less. That means the S factor is larger because S factor is 1 over the slope. You see the off current is much larger because here you remember this is in log scale. So any shift means exponential shift. That means this is exponentially larger. So the S factor will determine the off current, and you prefer smaller S factor, more steep slope. That is a better technology. So here, let's look at what determines the S factor. So S factor by definition is this 1 over slope, and you can rearrange the terms using the chain rule in the calculus. So basically you can split this into 2 terms, and then you can have the dv partial Vg over partial phi s, and then a partial phi s over partial log ID. So the phi s is the surface potential. So this is equivalent because you can cancel those two. So here the phi s is surface potential. Basically you have 2 components here. The first one is the gate voltage change respect to the phi s, the surface potentials change. This is like the gate to channel coupling, and we discussed that actually in one slide before. If you think about the voltage divider, we have. So this is the gate voltage you apply, and then this is the phi s. You have the COX, the gate capacitance, and the C depletion. So it's a ratio between the capacitor, between the cell X and C depletion. And if you spell out, it will be this one. So it's a voltage divider, and then use the voltage divider rule for the capacitor. So capacitor is different from the resistor, and the capacitors in series, means the capacitance actually should be added up. The capacitors in series, the 1 over capacitance should be added up. So it's different from the resistor. I've skipped the details, but if you do that, you want to get the phi s respect to the Vg using the cell X and C depletion, then you get this term. And then this is the first term, that is this one. And the second one is the string current change respect to the phi s. This is also what we discussed before. So this depends on the, think about the barrier top we discussed earlier, and you will have the exponential decay function due to the Boltzmann distribution of the electrons. So those electrons above the barrier can diffuse over. So this phi s will determine this exponentially. And if we take the log scale, then what is left is just in the exponential term. If you recall, the exponential term will have the, if you recall what we have before, it's like exponential q phi s over kt. This is the electron over the barrier. Or if we show the current, it also exponentially depends on the phi s. So if you take the derivative of the phi s respect to this current, then what is left is this kt over q. That is why you have the kt over q here. And then here this last term, natural log 10, is when you change the unit scale from this exponential. This is natural. This is a base e. The exponential function is a base e. Here we change to a base 10. So you need to change the units. That's why we have the natural log 10. This with respect to the base e. So this is what you can calculate. This is a number. It's 2.3. And the kt over q, is a thermal voltage, and it's 26 millivolts. So if you multiply the 2.3 and 26, you will get this 60 millivolts. At room temperature. Or in other words, this S factor is always larger or equal to 60 millivolt per decade. Why is that? Because you have the 60 millivolt, that is the physical limit. And in front of this 60 millivolts, you have this 1 plus something. 1 plus something is always larger than 1. At most, you can do equal to 1. So that means the S is larger or equal to 60 millivolt per decade. So this is true for all kinds of MOSFETs, no matter which technology node you are using. No matter this transistor is fabricated by Intel or by TSMC. So this is a physical limit nobody can overcome. So the S is always larger than 60 millivolts per decade. If you are good, then you are approaching the 60 millivolts. But in practice, in the real transistors today, typically use like 70 or 80 millivolts per decade. So this is the physical limit, And then this is the S factor. Why would this S factor matter? Because this S factor will determine the minimal threshold voltage you can have on the transistor. So think about that. If your transistor's on-off ratio you need is log ID, and you have the Vg. So the transistor I on versus I off, typically we need 10 to the power 5. So here, think about this current ratio. So if you need this current ratio like more than 10 to the power 5, because you want on to be on and off to be very off. So if you have 10 to the power 5 on-off ratio, this is required for your circuit. Then what is the minimal threshold voltage you can have here? So think about this slope. This slope tells you if you want to reduce the current by 1 decade, you need to reduce the voltage by S millivolts. And the best you can do is 60 millivolts. And here you want 10 to the power 5 on-off ratio. That means 5 decades. 5 decades. Each decade is 60 millivolts per decade. So here you will have 300 millivolts for the threshold voltage. At least you need to have 300 millivolts to maintain the on-off ratio more than 10 to the power 5. This is when you design your transistor structure very well, and your S can be as small as 60 millivolts per decade, but in reality, as we discussed, can be 70 or 80. So your threshold voltage can be like 300 millivolts to 400 millivolts. That's why today, for today's transistor, if you look at the specs, you rarely see the transistor's threshold voltage below 300 millivolts or 400 millivolts. That is minimal. So this is what we have to provide for the transistor to be functional. And that will limit the scaling of the transistor because you have to maintain 300 millivolts or 400 millivolts. That means this is for the threshold voltage. That means your gate voltage, the VDD, the power supply, needs to be above that. So for today's power supply, typically if you look at TSMC 7nm process, the power supply is like 0.6 or 0.7 volts. This is larger than this 300 or 400 millivolts because you have to make sure you turn on the transistor. So the minimal VDD today is like 0.6 volts. This is what you can do. You cannot operate the chip with like only 0.3 or 0.4 volts, 300 millivolts or 400 millivolts, because you have to turn on the transistor above the threshold, and the threshold cannot be smaller than the 300 millivolts or 400 millivolts because of this S factor, which is a physical constant. You cannot change it. Okay, any questions here? Okay, we talk about the practical limits for designing today's transistor because of this S slope. And also we can look at the S slope from the, let's say, the geometrical parameters point of view. So if you think about the MOS structure, this MOS structure. So if we bend down the band, if you think about the band diagram we have shown before. So this is the gate voltage you apply, and then this is a phi S surface potential, and then you have the VOX here. So it's like the voltage divider as we discussed. So you have the gate capacitance, and then you have the depletion capacitance. So if this is your gate voltage Vg, then this is your phi s at the surface of the silicon, and then this side is ground. That is the body or the substrate. So if you look at this diagram, it shows that if this silicon, this is the ground, this is like this part. It's ground, so it's flat, it's a reference. And now you apply the gate voltage to bend down the band a little bit, the delta Vg. And then you need to know what is the delta phi s, because not all the Vg applied will be translated to the change of the phi s. Only part of that is translated to the phi s. So here in this M factor we discussed before, this body factor is a ratio between this change of the phi s respect to the change of the gate voltage. So if you look at this geometry diagram, you will see that this is due to the voltage divider effect between the oxide and the silicon depletion region. So you have the COX and this C depletion. So that's why we have this ratio here. And actually you can replace the capacitance with the thickness of the capacitor. For example, here you know the COX is epsilon OX divided by TOX is the thickness of the oxide. And C depletion, that's in the silicon, is epsilon silicon divided by the depletion width WDM. And then if you replace the terms into this equation, and you know M is this one, then you will get this one. And the M is actually WDM plus epsilon silicon over epsilon OX TOX over WDM. And the epsilon silicon and the epsilon OX, you know the ratio is 3. This is the permittivity or dielectric constant. For the silicon is 12. For the silicon dioxide is 4. So this is 3. So that's why you have 3 here. So here our goal is to make the S as small as possible. So that means we want to make the, here, if you want to make this term as small as possible, you look at this one. Is 1 plus 3 TOX and WDM. You want to make M close to 1. So you can get 6 millivolts per decade. So you want this one to be close to 0. You see how do you design the transistor to make this 0. You want the TOX small and WDM large. And WDM is depending on the doping, Na. If you recall the lecture 8, you will see the maximum depletion width depends on the Na, the doping density. So that's why you can actually engineer your transistor if you want better S slope to give you better subthreshold performance, lower leakage. Alright, any questions here? Okay, last few minutes, let's quickly go over the band diagram for the non-channel device under the subthreshold region. So in the non-channel device, as we discussed, because the channel is non, so when you have the drain voltage applied, still the barrier top will not be affected. This barrier height is only modulated by the gate voltage. That is for ideal long-channel transistor, even though you have the drain voltage to push down the band for the drain. But the barrier top here is not affected because they are far away from each other, so this channel is none. So if the barrier height is not modulated here, that means when you apply different VD, the drain voltage, the subthreshold current will be almost the same because the barrier height does not change. So here we show example with the drain voltage 0.05 volts or 1.1 volts. You see the difference, and typically this is like in the linear region. This may be in the saturation region. So no matter saturation region or the linear region, the subthreshold current is almost overlapped with each other. So this is good device. This is a non-channel ideal MOSFET. But for today's short channel transistor, then it will change. Because now the drain is so close to the source. Then when you apply the drain voltage to push down the band, then the barrier top will also be reduced here. So then this is like the drain-induced barrier lowering effect, and we call it DIBL, Dibble effect. So if we consider this Dibble effect for the short channel transistor today, then if you draw the IDVG plot in the subthreshold, you will see that with different operation region, like this linear region, and this is saturation region, then because you apply the drain voltage, then the barrier top is reduced. You have more electrons move over, diffuse over. Then you have exponentially larger currents in the subthreshold. So that's why you see this shift of the curve. And this is called the Dibble effect. And the Dibble factor is typically defined as the threshold voltage change. So here if you think this is threshold voltage has a change delta Vt, then divided by the drain voltage change delta Vd. So for example here your delta Vd changed by 1 volt minus 0.05 volts is 0.95 volts. And the threshold voltage here change maybe by 200 millivolts. So you have this Dibble factor 200 millivolts divided by 0.95 volts. So this is not a good device. But this is what we have to deal with today with the short channel transistor. Because the gate lost the control and the drain can affect the source to the channel's barrier height. So the leakage current will be increased with larger drain voltage. All right, any questions? All right, so today's lecture, a quick take-home summary. So then what is important? Okay, so the IDVG plot in the log scale is important. Understand that below the threshold is a straight line, and then the definition of the I on and I off currents is important here. I understand this is non-zero, and this will determine your leakage current and the leakage power of the chip. And then understand the subthreshold slope definition, and understand the S has a lower limit that is 60 millivolt per decade. This is caused by the physical limits. And then understand the Venn diagram for the short channel device, where we have the source barrier stop affected by the drain voltage. That's why you have the increase of the subthreshold current. All right, any questions before we end? If not, then we are going to stop here. Thank you.